All right, hey guys, today we're going to be looking at how sixth graders understanding from one-step additive equations is going to connect them from the concrete to the representational to the abstract. So this is where kids have been living and using our algebra tiles. We have our x with our positive 3 units and it's equal to our positive 10. Now this is the concrete portion when kids have been hands-on manipulating it. And now we want to look and see how does that transition to the representational piece where they're actually drawing it. So this, which represents our one unknown, I can just draw using 1x. My positive 3's I can represent using 3 pluses. So I'm still modeling the same equation that's shown with algebra tiles, but in a simpler way for me to represent it on paper. And it's equivalent to my 10 positives, which I am putting into 2 rows of 5 to help students see the complement of 10. So my goal when I'm solving when I'm solving an equation is to find the value of this unknown that makes my equation true. One of the ways that I can do that is to isolate my variable. So right now it's on the same side with 3 positive units. So I'm going to create 0 pairs by putting 3 negatives on one side. And if I put 3 negative tiles on the left-hand side, I also need to put 3 negative tiles on the right-hand side to keep my equation balanced. And so I see that the positive and the negative right here will make a 0 pair. This will also make a 0 pair. And we have one more 0 pair. So I'm simplifying the left-hand side of my equation. Now I look at the right-hand side to see if there's any 0 pairs that I can simplify. And I have 1, 2, and 3 0 pairs. So if x is equal to 7 positives, and if I wanted to connect that to the now abstract view of solving this problem, when I have x plus 3 is equal to 10, by putting 3 negatives onto both sides, I put 3 negatives onto both sides. And then when I simplified my 0 pairs, that's me saying, hey, 3 positive and 3 negatives, that is one big 0 pair because any value in its opposite has a sum of 0. So I get that x is now isolated or by itself, and I had 10 positives and I'm taking 3 away, so I'm left with 7 positives. Now, this kind of problem also supports another strategy where we can decompose. So again, x with 3 positives is equal to 10 positives. And very similar to the numeracy routines that we've done with the horses and the elephants, I see that I have 3 positives on the left-hand side and I also have 3 positives on the right-hand side. So I can just take those away because I'm using the subtraction property of equality to still leave me with x is equal to 7 positives. What that looks like algebraically with our numbers and symbols is when I have my x plus 3 is equal to 10, I can decompose 10 into 3 plus 7. So I get x plus 3 is equal to 3 plus 7. And again, subtraction property of equality, I can take those 3's away to just give me that x equals 7 wholes. So we're going to take this thinking and now look here, which is still an additive relationship, only I'm adding a negative, which we can also represent as just subtraction. So we have our x minus 3, which I can represent using x and 3 minuses, and it's equal to 10 positives. So again, my goal is to find out what this unknown x value is, and I need to cancel out these negatives. I need to get rid of them so I can get the x all by itself, which I will do by creating 0 pairs. So I will add 3 positives to both sides to maintain balance. So what I've done mathematically is I've added 3 to both sides. My 0 pairs will simplify to 0, so this simplifies to 0. And on the left-hand side of my equation, I'm left with just 1 whole x. And on the right-hand side, when I simplify that expression, I had 10 positives and I put 3 more. So now I have 13 positives. So x is equal to 13.